This is the 7th lecture on we will complete the characterization of periodic waveforms, and we will also discuss elements of amplifiers. You recall that a periodic waveform x of t is such, it is periodic if and only if x of t is x of t plus n times capital T, where capital T is a constant and n is an integer, and capital T is called the period of the periodic waveform. A periodic waveform, a sinusoid, is a very common example of a periodic waveform. A sinusoid of the form A cosine or sine omega t plus alpha is a simple and a very frequently encountered example of a periodic waveform, of which capital T, the time period, is given by twice pi divided by omega. All right. To get a measure of a periodic waveform, well, you can display it on an oscilloscope. If you do that, then you get the complete picture. But and another way of doing characterizing a periodic waveform, which is sinusoid, is to specify capital A, the amplitude, the frequency omega, and the initial phase alpha. But if the periodic waveform is not a sinusoid, then you either have to display the complete waveform as on a CRO, or take some characteristic parameters of the waveform. And one of the parameters that we had discussed last time was the average value. That is, the average of the waveform is, let us say, if it is the current, if it is a current waveform, then IT dt integrated over one complete period. It could be 0 to capital T, or it could be any arbitrary time small t1 to capital T plus t1, that is the area under the curve for one period that is averaged over the period t. This is the average value. This is one of the parameters of a periodic wave. And as I had commented, if it is a sinusoid, then over a complete period, the sinusoid, the total area under the curve is 0, and therefore the average value strictly is 0. And therefore, for a sinusoidal waveform like I of t equal to Im sine of omega t, we may add alpha, we may not add, it does not make sense to talk about its average value if the average is considered over one time period, and therefore for a sinusoid the average value I average is considered over half the time period. Therefore it is 1 by t by 2 integral 0 to t by 2 Im sine omega t, and as you saw last time, the value is simply Im divided by pi. Is that correct? So twice Im by pi, this is the value. Okay. So the average is over half the time period, all right, for a sinusoid. But for all other waveforms, all other periodic waveforms, for which the average over a time period is not equal to 0, one usually speaks of average over one time period. For example, if I have a triangular wave like this, absolutely symmetrical and so on, all right, then what is the average value in the conventional sense? It is again 0, and therefore we talk of the average value over one half period, all right. So it is a matter of convenience. Average value over what period should be clear in the context of the problem, all right. Another parameter for a sinusoid is the so called effective value, and the effective value is defined like this. Suppose we have a current a current waveform I of t which is periodic, and suppose this current passes through a resistance capital R, then the power, instantaneous power dissipated in the resistor would be I squared times R, and over a small interval dt the energy that is dissipated would be I squared R dt. The energy dissipated over one complete time period 0 to capital T is this integral, and if I take the energy dissipated, well, if the energy dissipated in the resistor for one time period is equated to the same resistor through which passes a DC, let us say I DC, and it creates the same amount of energy dissipation, then the effective DC, then the DC value is called the effective value. So, if we wish to define, effective value is that direct current which passing through a given resistor produces the same energy dissipation as the periodic wave in one time period. All right, has it become too complicated? What we want is that we want to compute, due to the periodic waveform, due to the periodic current, the energy dissipated in a resistor, given resistor, over one time period, and then this energy is equated to an effective value squared, which is a constant, multiplied by R. This is the definition of the effective value, and you can see that I effective there must be multiplied by a capital T, agreed. All right, the total energy dissipated in the resistor due to a DC which is equal to I effective over a time capital T is I effective squared RT, and therefore I effective is equal to 1 over T integral 0 to T I squared T dt, capital R cancels, square root of this, and you can see that under the square root sign this quantity is the mean squared value of the current I. Okay, what you do is you take the area under the squared value, then you divide by the interval, therefore this is the mean squared value, and then we take the square root, and therefore this is the I effective is therefore the root mean squared value, and this is simply abbreviated as RMS value, RMS, root mean squared. You understand the interpretation of root mean squared value. This is the effective value, or that value of direct current which when passing through a given resistor produces the same dissipation as the periodic current in one time period. All right.
The concept of this I effective.
Yes.
Does it exist even when R is a function of something else, like it is a function of current or something?
It is a linear resistor. Yes. Your question is quite justified. When you talk of a resistor, it is implied that it is a linear resistor. The resistor is not dependent on current. It is a linear resistor. All right. Usually specify this as 1 ohm, but you see the value of the resistance is not important. But yes, it must be a linear resistor. All right. For a sinusoid, if I of t is equal to I sub m sin omega t, let us drop that initial phase alpha, it is hardly important. If for a sinusoid I RMS or I effective can be shown by carrying out this integration over one time period and then dividing by capital T, taking the square root. This algebra you can do yourself. It is given by Im divided by root 2, which is 0.707 Im, that is the 70.7% of the maximum value or the peak value. All right. In other words, if effective value is given I effective, then the peak value is given as square root 2 I effective, and when you say 230 volt AC, we mean the RMS value of the AC. So the peak value if you take a CRO and connect it to the mains power supply, then the maximum value you can measure will be 230 times root 2. This is true, I warn you, only for sinusoids. It is not true for other periodic waveforms. For other periodic waveforms you shall have to calculate by substituting in 1 by t integral 0 to capital T x squared dt, then taking the square root. You shall have to calculate for each case. It is only for a sinusoid that this shall be valid. That is, the peak value is root 2 times I effective. Now, according to these three measures, we have so far discussed three measures, that is the complete waveform for a periodic wave, the average value, the root mean squared value. All right. As I have told you, the total waveform can be displayed on a CRO. The average value, you connect any DC meter in the circuit, it shall read the average value. All right. The root mean squared value can be measured by any AC meter in which the torque developed which causes a deflection of the meter is proportional to square of the current or the square of the voltage. All right. And therefore so what we can display is the square, not the root, the square of the quantity. In actual meters, however, the meter is calibrated in terms of the square root of the values. That means it is calibrated to read RMS values, root mean squared values. So DC meters measure the average value, AC meters measure the root mean squared value, and if you wish to measure, a fourth measure is the peak value I sub m or that of a voltage V sub m, and the peak value is measured by a very simple device. What we do is, the periodic waveform, it could be AC or DC, it could be AC or non-alternating, let us say. You see, this is also a periodic waveform. It is not an AC because the sign does not change, but it is not a DC either. It is not a constant current. It is a pulsating current. It is a fluctuating current. So suppose I have a fluctuating voltage, let us say, and we wish to measure its peak value. Then what we do is we rectify this by means of a non-linear device, a diode, which passes current easily in the forward direction, and it does not pass current easily in the reverse direction. And then what we do is we take a capacitor. So what happens is, if this is a periodic waveform, then during the positive, well, not this, let us take an AC. Once again, what we are going to say is applicable to an AC in which the average value is 0. All right. What happens is, during the positive half cycle, this diode conducts. The diode conducts and the capacitor C charges. C charges till the voltage reaches this point. Then when this voltage goes down, the diode becomes reverse biased. That is, this voltage becomes greater than this voltage. So the diode does not conduct. It conducts only when the polarity of its drop is like this. That is, the left side is positive with respect to the right side. If the right side becomes higher potential as compared to the left side, the diode refuses to conduct, and therefore this capacitor then charges to the maximum value of the voltage V sub n. And if you put a meter here, a DC meter, it will measure Vm. So this is one way. As you will see, this is very much used in instruments to measure the peak value. To illustrate the concept of the root mean squared value, let us take an example. It is a very important measure of a periodic wave. Suppose we have a voltage Vt which is sum V0 plus root 2, it is a mixture as I had shown in the last page. It is a mixture of a DC and an AC, alright. The two are combined, root 2 V1 cosine of omega t plus alpha, alright. So we have a DC voltage which is V0 and an AC voltage whose peak value is root 2 V1, and therefore its RMS value is V1. Now what is the peak value of Vt? What is the peak value of Vt? Vt max, it is V0 plus root 2 V1. What is the minimum value of Vt? Okay, V0 minus root 2 V1. What is the RMS value of Vt? To find that out, it's a very simple formula, but let's derive this formula. Okay. To find it out, what we do is we square this. V squared would be this, and it would have three terms, a plus b whole squared. So it shall have a term V0 squared, it shall have a term twice V0 times root 2 V1 cosine of omega t plus alpha, and it shall have a third term which is twice V1 squared cosine squared omega t plus alpha. And to find, is that okay? To find the root mean squared value, each of these terms has to be integrated over one time period and then divide by the time period, capital T, that is, and the whole thing has to be square rooted. So if I say Vrms squared shall be equal to 1 by T, the first term is V0 dt 0 to T0, alright. Second term V0 squared, thank you. Second term would be 1 by T 0 to T0 twice root 2 V0 V1 cosine of omega t plus alpha, plus the third term, have I missed a square? No, 1 by T 0 to T0 twice V1 squared cosine squared omega t plus alpha. This would be my Vrms squared. There shall of course be a dt. Yes.
So why do we have this T0?
Oh, this is capital T. Thank you. This is inertia from V0. I wrote it T0. Okay, this is capital T. Now you notice that the first term is simply V0 squared, because integral dt is capital T, and therefore capital T and capital T cancel, it is simply V0 squared. Integral of the second term is 0, because it is a sinusoidal waveform integrated over one time period. Integral of the third term, this would be cosine squared omega t plus alpha dt integrated over one time period is equal to half. Alright, is this known to everybody? Is it known to everybody, or we have to prove it? Cosine squared theta is cosine 2 theta plus 1 divided by 2, and it is that 1 divided by 2 which brings in half, because the periodic waveform 1 second integrated over one time period is equal to 0, and therefore my final result becomes Vrms squared becomes equal to V0 squared plus V1 squared. That is it, as simple as that. And therefore Vrms is equal to square root of V0 squared plus V1 squared, and this can be extended to more than one sinusoid, alright, more than one sinusoid. That is, if we had another sinusoid of the same frequency or a harmonic frequency, then I could add other terms, V2 squared, V3 squared, and so on and so forth, alright. So the root mean squared value of a mixture can be very easily found out, with the restriction that the frequencies must be multiples of each other or the same. We either have the same frequency, because otherwise this averaging over capital T capital T relates to one of the sinusoids. So, the other sinusoids must be related to capital T, only then this formula shall be valid. If we have a different alpha, it does not matter, because cosine squared omega t plus alpha over one period, wherever you start alpha, it does not matter, one complete period. Alpha can be different, it does not matter. We then consider elements of amplifiers. By definition, an amplifier is a box, and any electronic circuit of which we are reluctant to look inside, what goes inside, we are only interested in the terminal characteristics. That is, if this is a two-terminal network, then we are only interested in the VI relationship. That is, if I plug in a voltage source, what current flows, or if I plug in a current source, what voltage is developed. If it is a four-terminal network or a two-port, then we are interested in, what we are interested in is, if we plug in a source here, what is the response here. All right. We do not want to look into what goes on inside. Then such a box in electronics is known as a black box. A black box is one whose terminal characteristics are important, not what is inside. Of course, there has to be something inside, and the purpose of this course, one of the purposes, is to find out what should go inside to be able to achieve a certain terminal performance, or the terminal characteristics. To realize a certain terminal characteristic, what should go inside. And an amplifier can be defined in terms of a black box, such that if I connect a voltage source VI at one of the ports, then at the other port the voltage developed is AVI, A times VI. All right. This is the definition of an ideal amplifier, that irrespective of what happens to the outside world, if we connect a voltage source VI here, an output of AVI shall be developed, irrespective of what is connected to these terminals. For example, we could connect a resistance RL. Irrespective of what else is connected here, we do not really care.
Is A greater than 1?
Not necessarily. In general, an amplifier, the term amplification refers to capital A greater than 1, but we can have amplifiers with less than 1. In that case, the amplification is negative, not negative, a fractional amplification. All right. These are ways of saying the same thing, that actually an attenuator, one which attenuates or reduces, can also be called an amplifier with a gain of a fraction. Capital A is called the gain of the amplifier, gain. Now, this irrespective of what goes on, what is connected here, this implies that the Thevenin equivalent resistance looking here shall be equal to, if the voltage developed here is AVI, irrespective of what is connected here, irrespective of the value of RL, what does it imply with regard to the Thevenin equivalent resistance looking back from these two terminals? 0. That is correct. So, this is one of the implications of an ideal amplifier, that the output resistance, this Thevenin equivalent resistance is called the output resistance. So, the output resistance shall be equal to 0. One of the other characteristics that is implied for an ideal amplifier is that the input current II is equal to 0 for ideal amplifier. Now, what does that mean? Input current is 0. This means that the equivalent resistance looking into the amplifier is infinite. So, it is not Thevenin. This is not Thevenin. Thevenin is this one. This is the input resistance. That is, if you connect a source here with, let us say, an internal resistance Rs, if you connect a source, let us say Vs, with an internal resistance Rs, all right, the current taken here is 0, then what would be Vi equal to? Vi should be equal to Vs, isn't that right? So an ideal amplifier disregards the internal resistance of the source, internal resistance of the input, okay, it does not respect, it has no respect for the internal resistance of the source. Whatever the internal resistance, it develops a voltage equal to the voltage that you wish to amplify. And as I said, the output Thevenin resistance is equal to 0 and therefore an ideal amplifier can be modeled, an ideal amplifier can be modeled like this, that you have a source Vs and an internal resistance Rs. This is connected to the ideal amplifier, all right, and the ideal amplifier produces a voltage V0 is equal to a Vi, whatever be the resistance connected to this, which means that it behaves like a voltage source of value A times Vi with this polarity, all right. The internal resistance or the Thevenin resistance is equal to 0 and therefore it behaves like this. You see, this is an example, this is Vi, this is an example of a voltage controlled voltage source. Here is a voltage source AVI whose voltage depends on another voltage, and therefore this is a voltage source whose voltage is controlled by another voltage V sub I. So it is called a voltage controlled voltage source, VCVS. Now in practice this is not the case. As I said, ideal is ideal. A practical amplifier shall differ from this ideal characteristics by having an input resistance which is not infinity, input resistance which is finite. In other words, a real amplifier takes in a certain amount of current. I sub I is not 0, it is non-zero. Similarly, the output resistance of a real amplifier is not 0, but it is a non-zero quantity, and therefore if I consider a real amplifier, the model of a real amplifier shall be like this. You have a source Vs connects to the real amplifier, okay, in which the input impedance, input resistance is not infinity, but let us say some value Ri, then this voltage developed is Vi. Now you see Vi is no longer equal to Vs because there is a drop in Rs, all right, and the current taken here is no longer equal to 0. It is given by Vs divided by Rs plus Ri, all right, and the output, it is a voltage controlled voltage source AVI, but it does not come with an internal resistance of 0, it comes with an internal resistance of R0, and these are my load terminals to which I can connect a load RL. This is the picture or the model of a real amplifier, and is that being a bit fast? Okay. Yes or no? It cannot be in between. Okay.
Yes, sir.
All right, we go slow. you understand this model for a real amplifier. In an ideal amplifier, all that you have to do is to make this resistance infinite, so that no current is taken by the amplifier, and you have to make this resistance equal to 0, so that the output voltage is equal to a Vi irrespective of what you connect here. Now, in a real amplifier, if you want to find out V0, this voltage V0, then you notice, I cannot write here, you notice that Vi, well, V0, the output voltage that is developed across the load RL, is a voltage division between R0 and RL, and therefore this is equal to a Vi RL divided by RL plus R0, all right. And Vi is the voltage division of Vs between Rs and Ri, and therefore Vi is equal to Vs multiplied by Ri divided by Ri plus Rs, and therefore V0 is equal to a Ri divided by Ri plus Rs multiplied by RL divided by RL plus R0, and this multiplied by Vs. Therefore, the gain G of the real amplifier, which is equal to V0 by Vs, is given by A times Ri divided by Ri plus Rs times RL divided by RL plus R0. This is the expression for the gain in a real amplifier. How is this gain modified? If the amplifier was ideal, then the gain would have been simply capital A. All right. Ideal means what? Ri goes to infinity, so infinity divided by infinity becomes 1, and R0 becomes equal to 0, so RL divided by RL, that also becomes equal to 1. All right. So, in a real amplifier, the gain shall always be reduced as compared to the ideal case, and a real shall approach an ideal. A real amplifier shall approach an ideal if Ri is much greater than Rs. All right. It does not have to be infinity, but Rs is so small. For example, if Rs is 100 ohms and Ri is 1 meg, well, what does it mean? The ratio then becomes 100 divided by 100 plus 10 to the 6, which definitely to an electrical engineer or any other engineer, which definitely is very nearly equal to unit. Yeah, that is what I said. Oh, I beg your pardon. It is 10 to the 6 in the numerator divided by 10 to the 6 plus 100. What is 100 to 10 to the 6? It is nothing. All right. And therefore, this is approximately 1. Similarly, what you need is that the load connected to the output RL should be much larger compared to R0. Once again, 1:100 for example is good enough. All right. So, your amplifier design, your motivation or your objective should be to make as high input resistance as possible and as low output resistance as possible. This output resistance is obviously the Thevenin equivalent resistance. An amplifier which comes very nearly equal to an ideal amplifier is the so called operational amplifier, which is available as an integrated circuit chip, IC chip, a small multi-terminal component. Actually, there are 8 such components. Let me first give you some familiarity with the actual chip. The actual chip is an 8 terminal. 8 terminals are provided, and the symbol for an operational amplifier, I will explain why it is called operational a little later, but the one chip that is most popular is the so-called 741 chip, 74. Sometimes there is a mu A or Li, this indicates the company which manufactures, but the generic name for the op-amp which is most popular is 741, and 741, as I said, comes with 8 pins, and these pins are numbered like this. Pin number 2 is an input connection, pin number 3 is also an input connection, pin number 2 is called inverting input terminal and a minus sign is included here. Pin number 3 is called non-inverting input terminal, and the significance is that if you provide an input at pin number 2, the output shall be phase reversed. That is, if you put a 1 millivolt signal here, the output shall be minus, let us say, 100 millivolt if the gain is 100. Is that clear? There is a phase reversal. If you put a sin omega t here, the output shall be proportional to minus sin omega t. On the other hand, non-inverting terminal is one which preserves the polarity or the phase of the input. That is, if you put a plus 10 millivolt here, the output shall also be a positive voltage. All right. The output terminal is the terminal number 6. Output terminal is the terminal number 6. There are 2 inputs, 1 output. You require other terminals for power supply connection, and the power supply, any electronic circuit requires a power supply, a DC battery to be connected, and the power supplies terminals are 4 and 7, and a typical 741 requires a power supply of 2 kinds of polarities, that is a positive one as well as a negative one. Typically this could be 12 volt, plus 12 and minus 12, and the middle point of this power supply, you understand what this is? This is a series of, I am showing this is a series of batteries. This is actually a rectified AC which is available in the laboratory in the form of a box, and it is called power supply. All that it supplies is DC. Typically it could be plus 12 and minus 12. The middle point of the supply is the reference potential and is connected to ground. All right. As far as amplifier characterization is concerned, 4 and 7 do not come into the picture. All right. 4 and 7 have to be connected to a battery, otherwise the circuit does not work. All right. There are other terminals which are 1 and 5. We shall learn later what the purpose is, but for the present we let it suffice to say that 1 and 5 pins numbered 1 and 5 are for offset nulling. We will explain these terms later in great details. You just hear the term now, so that when I mention it again you will remember that yes, this was spoken of. And of the 8 pins, there is another pin 8 which is marked NC, that means no connection. If you want to connect another resistance, for example, this provides a port or a terminal to which you can connect. All right. So 8 is NC, and this is a typical. Pardon me?
So does it provide a port or a terminal?
It provides a terminal. It provides a terminal, but between 8 and the power supply ground, it provides a port. This is obviously external. The 741 chip provides no ground. The ground has to be provided externally by means of the power supply. So the reference is set outside the chip. All right. So this is 741, and if I represent this now in a simple form, all that we are concerned with is the input and the output, because we refuse to look at what goes inside. So the terminal connections are, we also forget about the pin number and all that. We have 2 terminals and an inverting input terminal, to which let us say we apply a potential Vn, a voltage Vn, and a non-inverting input terminal to which we apply a potential Vp, and all this is measured, these potentials are measured with respect to some ground. Alright, these potentials are measured with respect to some ground, and the output voltage is V0. Then the op amp, operational amplifier, is characterized by a gain A, capital A, such that the definition of A is that V0, the output voltage, is A times the effective input voltage, that is the input voltage between these two terminals, which will be Vp minus Vn. Alright, this is the definition of an op amp gain. As you see, capital A is a positive quantity, capital A is a positive quantity, so that if there is no Vn, if Vn is 0 and there is only Vp, the output V0 is equal to A times Vp, which preserves the polarity. On the other hand, if Vp is 0 and you apply a voltage at the inverting terminal, then the output becomes minus a Vn, which changes the phase. So if you apply sin omega t, it would be minus sin omega t. There is a change of phase by 180 degrees. Is that clear? The purpose of these two terminals is to make additions as well as subtractions, to have inverting gain. For example, if you have 1 millivolt and you want a plus 1 volt out of it, then you can apply to the non-inverting terminal. On the other hand, you might require a negative, a minus 1 volt, then you apply the input to the inverting terminal. Alright, so it is a more versatile chip or amplifier chip than the conventional amplifier, where there is only one input and one output. There are two inputs here which can change the sign of the given input voltage. Implied in this definition, now let us look at slightly further. Implied in this definition is that the current taken by the amplifier at both inverting and non-inverting terminals ideally are 0. That is, In is equal to Ip equals to 0. What does that mean? It means that whichever input terminal, from whichever input terminal you look into the amplifier, you face infinite resistance. Ideally, this should be the case, and a real op amp chip is not far from this idealness. Typically, the input resistance is of the order of a meg, 10 to the 6 ohms, and ordinary sources, like if you want to amplify, let us say, public address, the signal picked up from a microphone. Well, microphone will not have an impedance more than, let us say, 1K. So compared to 1K, it is 1000 times larger, alright, and therefore the input impedance is infinite. Ideally, In and Ip are equal to 0. What would be the impedance looking between Vn and Vp? Once again, that shall also be infinity, alright, and V0, the output terminal, the effective resistance looking into the amplifier, ideally is equal to 0. In other words, what does that mean? It means that the output of an op amp can supply infinite amount of current, isn't that right? If the output resistance is 0, then you can draw almost any current from this, which obviously there is a fallacy, isn't that right? What is your source of energy? These two batteries. Now you know that batteries, they have a limitation, they cannot supply more than a certain value of current, and therefore an ideal is ideal, but for the limited purposes of instrumentation and control, the ideal characteristics are almost always valid, and therefore we usually treat an op amp chip as ideal. unless it is a critical application where we shall have to look into the sources of non-idealness. Let me quickly give you certain practical applications of an op-amp to give you a feel of what an op-amp can do and what an op-amp cannot do. Or before that, I must explain the term operational, why it is called an operational amplifier. Well, the choice of this term is for historical reasons. It is a bit unfortunate because the modern 741 can be used in many operations rather than what it was meant to be with the adjective of operational. Operational amplifier in old days when transistors were not invented, the integrated circuits were not available in the market, they used to be made for analog computers. Digital computers were not known or were in a very rudimentary form. Analog computers were very much in vogue, they were very popular, and what people used to do is to take vacuum tubes and configure them in an amplifier configuration such that it could perform operations like differentiation, like integration, like limiting, like amplification, like nonlinear, even nonlinear characteristics and so on. So this is why the term operational, the adjective operational was given to such amplifiers. One of the characteristics that I have failed to mention is that capital A, the gain of the op-amp chip, is very large. It tends, ideally it tends to infinity, and very large in the context means a gain of the order of 10 to the 5 or higher. So if capital A is greater than 10 to the 5, and in very good op-amps, it could be as large as 10 to the 6 or even higher. All right, so it's a very large gain. Now with the advent of transistors and integrated circuits, the amplifier that replaced the vacuum tube operational amplifier was 741, but it was still called an operational amplifier, and history cannot be forgotten, and therefore the term operational has continued, and it is simply called op-amp. The term operational is in a sense more valid now because this 741 chip can perform many more operations than their poor cousins, the vacuum tube operational amplifiers, which existed in the 40s, for example. So in any case, we shall call it simply operational amplifier, op-amp, or sometimes we shall call simply an OA. Suppose you have an OA, just to get a feel of what an OA can do, you have an OA with the non-inverting terminal grounded, all right, and the inverting terminal is connected to a resistance, let us say Ri, and there is a voltage Vi connected here. In addition, there is a resistance Rf connected between input and output, and this voltage is V0. Okay. Suppose an operational amplifier is connected in this configuration. Now because capital A tends to infinity, this voltage, the voltage that appears between the two input terminals, you know V0 is equal to capital A times Vp minus Vn. Now if capital A tends to infinity, then what is Vp minus Vn? That must be equal to 0, very nearly equal to 0, which means that the potential of this point must be approximately the same as the potential of this point, which is 0, and therefore this point, although not connected to ground, behaves like a ground, and therefore this point is known as a virtual ground. Okay. Capital A in practical op-amps is extremely large, of the order of 10 to the 6, and therefore Vp minus Vn is equal to V0 by A, this tends to 0 because capital A is very large. Therefore, Vp is approximately equal to Vn. That is, the two potentials of the two input terminals are approximately equal. Now, one of them has been connected to ground, so its potential is 0. Therefore, the other must also be 0. Now, you see, this is a 0 potential point, but not connected to ground. So, it is not a real ground, it is a virtual ground. This virtual ground concept simplifies the analysis of such amplifiers tremendously. For example, in this circuit, if I draw it again, this is ground, Ri and Rf, this is Vi. You see, if this is virtual ground, then what is the current here? Vi by Ri. Okay. Now, the amplifier is ideal, so it does not take any current. So, this current must flow like this. This current has no other way, by KCL it must flow like this, and therefore, this current shall be equal to the potential difference between this point and this point is minus V naught, because this is 0 potential and this is V naught. So, it is minus V naught divided by Rf, and therefore, V naught by Vi, which is the gain of the amplifier, the output voltage divided by the input voltage, is simply equal to minus Rf divided by Ri. And you see, the gain now is inverting, there is a negative sign here. That we expected, because we are applying our potential to the inverting terminal. But what is surprising is that the op-amp parameter capital A does not enter into the picture at all. In fact, the op-amp parameters do not, none of the parameters enter. Why? Because we made that assumption that the op-amp is ideal. Now, the gain is therefore determined by simply a ratio of two resistors. The significance of the subscript should now be obvious to you. Capital F stands for feedback. That is, feedback is the path provided from output to input. From input to output is feed forward. Now, if something comes back, you see, something comes back through this resistance, a current, it is called a feedback resistor. We shall understand the meaning of feedback in much greater details later on. But as well, this is the feedback resistor, and Ri, this subscript I stands for input resistor. All right. So, it is a ratio of two resistors only. For example, if Rf is 10k and Ri is 1k, then the gain would be minus 10, and it is determined by these two resistors only, nothing of the op-amp. Op-amp only helps to stabilize the gain to minus 10. The other interesting feature is that if this current is denoted by I, then what is I? I is simply equal to Vi divided by Ri, and therefore, what is Vi divided by I? It is simply equal to Ri. So, the input resistance that is faced by the source is equal to Ri. That is all. You see, the source is here. The source is here. So, the input resistance seen by the source is Ri. It is also independent of the op-amp. Okay? And if that is so, then we can make a very useful analysis, that is, Vi is equal to I times Ri, and V0 is equal to minus Rf divided by Ri times Vi. Therefore, this is equal to minus Rf times I. Is that correct? The op-amp, therefore, between this point and this point, I include the input resistance, that is Ri, can be modeled in a very simple manner. That is, we have a Vi, from Vi we have created a current I. How? By connecting a resistance Ri, this current is I, and then the output voltage V0, it acts as a voltage generator equal to Rf times I, with what polarity? Minus here and plus here. So, this is V0. Now, what can you say about the kind of model that we have here? It is a current controlled voltage source, isn't that right? This is a voltage source RFI, and it is controlled by current at another location, and therefore this is a current controlled voltage source CCVS. All right, this is a simple model. We shall continue this discussion. Plus minus, because this has been shown as minus plus. If you write V0 in terms of RFI, it is V0 equal to minus RFI.
Sir,
yes.
So is it not possible that V0 is also very large?
V0 can also be very large, but the practical limitation is that V0, the output voltage, cannot exceed the power supply. When it exceeds the power supply, the output gets saturated, that is the nonlinear region of operation comes into play. All right. V0 cannot extend beyond 12 volts, let us say, typically plus minus 12. Any other question? Thank you.